Alrighty, it's recording now. And that's the wrong screen. I guess I'll have to cut that out. Okay, cool. All right. Hello, everybody. Welcome back to How to Become a Senior Engineer, episode 2. We are here today with Gitesh and Rajeev once again. You guys can say hello.
Hi everyone.
Cool. And yeah, we'll just go ahead and get started. So the topic of today is thinking algorithmically, which is a super important topic because I'm a big believer that before touching the code, you should have the full algorithm in your head and know exactly what you're going to do. Now, of course, that's an aspiration because it's almost impossible to consider everything, but the more you consider, the better your code will be. And ultimately, the better your code is, the more difficult of a product you can build. So almost like how good your mental algorithmic skills are is the limiting factor in what you can build when it comes to code. So one quick thing from last time that I just want to reiterate is this idea of what is programming, because we should probably remember it every time. It's again, the most important part is you're taking all of this complexity, all of these vague notions in your head, and you're turning them into very structured thinking. So in other words, algorithmic thinking. And just to remind as well, good code has to be these three things: safe from bugs, it works; easy to understand, anyone can read it and just pick it up immediately; and then RFC, ready for change. So that kind of goes with the simplicity and elegance of something that's easy to understand. You can change it quickly and easily, and you're anticipating it might be changed in the future as you're building it. So that was all part of this test-driven framework that we've been working on. I guess we can call it the Mora process, but really it's from this 6005 class at MIT. But last time we talked about the PRD, the testing PRD, which is what you guys made, and we can probably have like another episode going over the one you guys made, maybe tomorrow or something, because it's going to be a pretty good example, I think, once it's complete. But anyways, that was last time. This time we're going to focus on the steps 2 and 3, which are the algorithmic thinking. So writing the pseudocode, determining what the behaviors should concretely be of the feature you're trying to build. And then once you understand the algorithm behind everything, you can actually go into this design document, which is a concept that I kind of took from Google, which is basically this document where it's not exactly code, but you lay out the components, the functions, the files. I like to personally write every function that I plan on writing, or at least the major, most important functions. If something is easy and everyone knows how to do it, like sorting an array, you don't have to write that, obviously. You can just write sort the array. The higher level, the better, really. But all of the custom logic you're doing, I like to write every function and then so the control flow, then every if statement after that. Like, if this condition, then we do this, otherwise we do this, and have the nested blocks in the document. That's been working for me, just writing that in English and in pseudocode. So we'll focus on these. And again, like I always want to reiterate this, but the most important thing that we're trying to do is in our own head, create order. It's all about order, structure, and clarity. And it's a repetitive process. Like, at least I find myself a lot of times repeating the same things over and over again, revisiting the same problems in my head. And that's really the whole point, because when you're coding, ideally, every time you're writing code, you're never coming across a point where you don't know what to do next. If you're ever writing code and you don't know what you're doing, that's sort of like you haven't thought through. Basically, what happens is you reach the point where you haven't figured out the solution already while you're coding. And that's generally not a great sign, because if you overlooked something, that's fine. Everyone overlooks things. But if this happens too much, you end up making a lot of ad hoc solutions, which is what we're really trying to avoid. We don't want to make ad hoc code all the time. That's when it gets really messy and complex. We want every line of code to have a purpose behind it. So the whole point of algorithmic thinking is think of the problem so much ahead of time, design the problem so thoroughly, write documents, write notes, write diagrams, do all of that just so that in your head, the most important thing is in your head, you have the order and the clarity and the structure you need. And then once in your head, the solution is already clear, it's very easy to go and just write the code. In fact, if Sometimes you don't even have to think when you're writing code because that's how clear it is in your head. You almost already know what you're doing. And that's the state that you want to get to in whatever it is you're building. So here, I just want to go over some tips. Like mainly this video, I think will be a lot of tips about how to think algorithmically and do it effectively, because that's at least something I had a lot of experience with. I did physics in my undergrad, and then I also did computer science. I double majored, and when I did computer science, my main focus was on algorithms. So I took the advanced algorithms class, I took the regular algorithms class, I took the distributed algorithms class, the quantum algorithms class. So I was always doing algorithms, and it was very hard at first. I think it's really hard for everybody, but there were some strategies that really helped me get better at it, and perhaps it can apply to others. So one thing that I always think to myself when I'm doing any kind of algorithms is that there's always a solution. No matter what, there is a solution. Whatever the problem is, whatever feature you're trying to build or whatever product requirements there is a solution. Because I think it's very common that people do this. They have a product requirement, they try to figure out how to build it, they encounter a lot of difficulty, and then they start believing, oh, this is impossible, or it's not worth it, or whatever. People will always come up with reasons why they shouldn't do it. And then they go back and modify the product requirements. Uh, Very rarely that might be what you have to do, but generally I'm completely against that kind of thinking. I think what we should do is when you want to build something, that is what you want to build. Don't budge. You need the perfect quality, the ultimate quality. Never budge on quality, never budge on the original vision. Just do the work to figure out the solution, no matter how technically complicated it is. And that mindset helps you build really nice things, like really solid code and really good products ultimately. So when you reach that point where you're feeling really bad and you've been stuck on a problem for a long time, there's a lot of strategies, of course. You can go and take a break, come back to it tomorrow. Don't pressure yourself with time. Sometimes you have to, of course, but time is really what gets people to decrease on quality. I mean, this is what Steve Jobs said once. He said that uh, to make something extremely high quality, all that it takes, it's not more talent, it's just a little bit more time. And most people don't spend that little bit of extra time to make it really high quality. That's what he said, and I think it's totally true. So definitely don't pressure yourself on time when you're trying to solve an algorithm. And the most important thing for me is always remember this, there is a solution. You will be able to find it. It's not going to be in vain, all of the effort that you're putting in. So it's hard and it takes time, and that is to be expected when you're solving a very difficult problem in a good way. Oh, and I kind of like this thing I put at the bottom too. Become the problem. You have to make this problem be a part of you. You know it inside and out. And I like to think of problems like people too. I mean, you can even fall in love with a problem. And a lot of people do, like mathematicians famously, they'll fall in love with a problem and work on it for 10 years. It's incredible. And that's when they come up with really cool solutions. But it's like a person, get to know the complexity, come up with your own names for different parts of the problem, come up with your own concepts, your own words and your own thoughts. You're almost like an explorer in this new space. Can be pretty fun. All right. And here's another thing. So when it comes to building products, right now we're in the stage in the world where most of the problems in computer science that you have to tackle, usually people have not tackled them yet, or at least not very many. So you're coming up with let's say new ideas. You're coming up with new solutions and new concepts all the time when you're coding. So how can you do that quickly or effectively? How do you go from these random ideas, which you might be unfamiliar with, to a point where you can very quickly and effectively work with these concepts you're creating? And to me, I believe the most important thing, it's a little bit obvious, it's to use the tools of math as soon as possible. As soon as you hear a new problem statement for something you want to code up, as soon as possible, try to use pattern recognition and determine this is a graph. This behaves like a tree. this is an array. Because the faster you do that, in abstract algebra, there's a concept called homomorphism, which is when one system can be, through a rigorous set of rules, transformed into another system. That's basically what we want to do. We want to map the problem onto an existing problem that we already have the solution for, or at least that we already have many concepts for, so that we can think about it more effectively. And if you do that, then you basically will be able to gain a grounding in your own mind and have many tools. And of course, it might not be a perfect mapping, but if the mapping is 60% and you can come up with 40% new ideas, that's a lot easier than coming up with 100% new ideas for everything and reinventing the wheel. So just like in code, we use libraries to solve problems that already exist. When it comes to algorithms, you should use the libraries or the pre-existing concepts of mathematics to solve problems that have already been solved as fast as possible. And ultimately, you can create your own frameworks. So I put some stuff down here. Like we were just talking about the lexicographic C tree, the CRD key tree. So I also created some AI framework called the TRMG, Temporal Reflective Memory Graph. So it's actually pretty fun if you think of it that way. You use the tools of math, and then almost like being an open source developer where you can create a new library, you can create your own mathematical frameworks and maybe one day in a paper write them or just share them with others. In general, I mean, I guess maybe it's not for everyone, but I personally love doing this. And I think if you want to be a really good engineer, especially a senior engineer, you should be good at math and you should enjoy doing it. And that kind of stuff is great. So this book is one I definitely recommend. It's commonly known as CLRS. I mean, you can't really see because the picture is so low resolution, but those are the author's last names, CLRS. And it's an extremely good algorithms book. I mean, it's called Introduction to Algorithms, but at MIT, it was actually the textbook for the advanced algorithms course. So it's I mean, there are some easy algorithms for sure, but it has a lot of depth. I would definitely recommend this book for anyone who wants to be a really good engineer. Then beyond that, probability is generally a great mindset. If you can do probabilistic thinking and probabilistic problems, these kind of combinatorial problems as well in discrete mathematics, uh, that is a really good mindset for computer science because there's a lot of overlap in the concepts in combinatorics with computer science. So people like all the quants, the quantitative researchers love probability problems. It's what they always ask you. And then one more that I have to put in here because it's what I am. I'm a physicist. Like technically that's my main education. So there's so many useful tools in physics too. I mean, it's mainly the tools of algebra, but especially if you look into statistical physics and thermodynamics, you'll find there's a lot of overlap with combinatorics and a lot of interesting and useful concepts in there as well for working with computer science or software engineering. I mean, one concept that everybody talks about now is entropy. And entropy is a concept from physics. And even when we're talking about taking disordered ideas and turning them into structure, I always frame that in the ideas of entropy. I think it's about entropy increasing or entropy decreasing. And all the machine learning people tend to talk about entropy, which is an idea that comes from physics. And in fact, I think that machine learning in general is a field that is very, very closely related to physics because in physics, we do a ton of matrices in linear algebra. That's pretty much how you describe almost any system in physics. And these are differential matrices. So it's linear algebra calculus is mainly what you're doing in physics. And that is exactly how machine learning works ultimately as well, with standard gradient descent and backpropagation and all of these sort of concepts. So I do have to recommend the ideas of physics. And these are just things to look into beyond the standard computer science curriculum, so to speak, to get better at algorithmic thinking. So once you get really good at this kind of thinking, it does become easier. And eventually you start creating this intuition, which to some extent, I think you guys already have, I'm sure of it. But basically, the better you get, the more powerful your intuition will become. And pretty soon, you'll be able to realize just by thinking, when you're in this like algorithm creation thinking stage of the problem, you'll be able to realize what is actually a good solution versus what is not, just by feelings, not by exactly going in and doing all of the work and seeing it, but just almost on prejudging. And that's super important because if you're doing a really complex problem, you don't have time to go into every individual branch of the tree. You shouldn't try to do a DFS, basically, because there's just way too many possibilities if you're doing a hard problem. If you're doing an easy problem, it doesn't really matter. You can try everything or you can do it in one shot. But if you're doing a complicated problem, then you basically want to cut out the possibilities that are bad ideas as soon as possible and only explore the most promising ones first. And the way you can start telling what that is by building this sort of intuition muscle. So it sounds a little weird, but whenever I'm creating algorithms for something complex, like what we were talking about before the video, which is like this real-time collaborative system, I'm always thinking first, is this an elegant solution? Does this feel right? Does this look beautiful? Is it simple? Does it feel powerful? These are abstract concepts, right? It's not really a mathematically defined thing, whether a piece of code is powerful or simple or beautiful. But I do find myself often being able to tell whether or not code is or an algorithm is elegant or beautiful. And that helps me a lot in determining what is the right path to go down versus what is a path I should ignore. And so far, really honing that intuition has helped me become better at creating algorithms, basically, and ultimately better at coding. So I definitely recommend that you guys try to perhaps think in a similar fashion if it works for you. All right, so ultimately, the whole point of all of this algorithmic thinking is we should be designing algorithms ourselves, almost like a math problem that you do in school, so that the reason we do that is so that eventually we have in our head all of the knowledge and structure necessary to write the code. But I don't think you should go straight from algorithm to code. You can, but it's not really the easiest thing to do, and it's generally not what people do on teams either. I think the best idea is to create this design document first. And basically, when you should make the design document is once the solution is already in your head. So once you do the algorithmic thinking, once you feel like you understand the problem super well and you understand the solution super well, then you should start to write down in this design document a lot of the high level concepts of the code. So what that would be are things like the functions, how the functions behave, important variables. I really like writing inputs and outputs. I find that that helps me a ton. So basically, like, what is the signature of this function? What are the inputs? What do they all mean? What are the possible inputs? That's always where I start, honestly, when it comes to the design document. And I really believe that that is why there are statically typed languages, basically, because they force you to understand what are the inputs of a function before even writing it. So I do think that's whether or not people say it, I usually don't hear people saying it. I do think that is implicitly one of the main benefits of statically typed languages and why they even do it, because you have to think of the inputs. So I always write the inputs of functions. I always write all of the possible inputs and what they mean. I can show you some examples after the video too, and go a bit more into that like backend document. But then beyond that, it's also very useful, in my opinion, to write just pseudocode in English for every function and what it's going to do in this design document. But it's an iterative process. It's a collaborative process. So you do it with the whole team, basically, and everyone comes together and tries to understand what it is we're going to code from this design document. So I think that's basically what I was talking about right now. Once you have the algorithm in your head, you can start making the design document. And the solution should be in as much detail as possible. So there's really no correct way to write a design document. You can do it in 1 day or you can do it in 10 days. Like I was mentioning to you guys, it took me like 5 days to determine how to build that collaborative real-time system. And that was before I even touched code. So I was basically making the design document for 5 days. Although the first day was only on my iPad, writing by hand, basically notes and diagrams and small things like this. It was very unstructured back then, but then over time, it eventually became very structured into the design document. And then I used that design document to then make it even more structured inside the code itself. And then the code for this collaborative system goes between a backend on AWS, a front end on the computer, and even in AI as well, because the AI has to do certain things in real time, and that's a whole separate repo. So the code is split between three different repos and many different microservices and many different technologies, many different stacks, many different, there's so much complexity in the code. However, it all makes sense to me because it's the same algorithm. It's just an implementation of the same concepts that I already designed and determined. So that's really the power of being able to architect code in this way. And the last thing that I really want to reiterate is before writing the design document, the solution should be pretty well formed in your head already. So that's why this is two steps. If we go all the way back to the beginning, there's, the TPRD is one step. You're just writing that document, and at the same time, you're thinking about what should the product do. If you want, it can be two steps, but for our case as engineers, we can make it one step. For a designer, it would probably be two steps. But for us as engineers, this algorithmic thinking portion is really two steps. The first step is abstract in our head, understanding and creating knowledge in our own brain. The second step is creating the document that is the final form of the knowledge. And I really believe that you should only make the document when you understand the solution super well, when you are confident in it, when you feel good in it. And of course, it always happens that you're going to overlook details. You'll even get to the code and you'll overlook details. But the problem is this. If you overlook too many details, by the time you get to the code, you're going to get lost in it. And maybe you have to start over, or maybe you give up and you don't solve it because you feel like it's impossible. That's really what happens. People give up and they can't build it. So that's the risk you're running if you go in not prepared. And then, of course, maybe you try again, maybe you work on something else, who knows? But you don't end up building what you set out to build, which is kind of the problem. So I think it's very important to be fully prepared at each step along the way so that at the end you can go all the way through to completion. So basically, write the document once you're already very sure of the solution algorithmically in your head. Then you write the document, and then it's finally time for implementation. And that's the actual coding and how to do that once you have the design document. So that's everything for today. Thank you guys. Cool.